session of our Earth Science Meets Data Science workshop for Goldschmidt, looking at the services and systems, policies and procedures, and tools and techniques for geochemistry. Our next talk is going to be by Dr. Marshall Ma, Dr. Chao Ma, and Dr. Xiang Cui from the University of Idaho. And they're going to be telling us about geochemistry through space and time with spatiotemporal weighted regression model that they have developed. So with that, I'm going to pass it over to, I believe Chao Ma is going to be the primary presenter sharing his screen. Chao, are you able to share your screen?
Yes, thanks, Shona.
Perfect, thank you. Take it away, Chao.
Okay. Can you guys see the presentation here? Hi, Shona, can you see?
Yeah, I see it.
Okay.
It's all good.
Okay, all right. Okay, today I'm going to show you the spatiotemporal weighted regression, the algorithm that we developed. And first I'll give some background introduction and then show you how to use this algorithm and the code. Okay. So my presentation will be introduction methods, experience with the simulated data and the real world data. So we know in the real world, in the geographic problem, there are three important entities: time, space, and attributes. But sometimes you can use the ordinary least square to get the regression model globally. But however, there are some local spatiotemporal variation that is not consistent with the global model. So that means that is called spatiotemporal non-stationarity. So as this figure shows, say the house price are affected by two variables. And associated with the two variables, there are three coefficients, bet 0, which is the constant, and bet 1 and bet 2. In the global least square model, they treated these bet 0, bet 1, bet 2, these coefficients as the same across the space. But what if their value are not consistent across the space? This is spatial heterogeneity. Hold a second, let me change the pointer. Okay, it's called spatial heterogeneity. So how to solve this problem? We developed an algorithm called spatial temporal weighted regression. So it is the strategy of spatial-temporal distance decay. Because according to Tobler's rule, everything is related to everything else, but near things are more related than distant things. Here, to solve the heterogeneity, we have to find some local range that within this range, everything, all the observation points are affecting the regression point. So here are the 4 time slices. T is the present time, and T minus P, T minus Q, T minus S are the previous times. So that these are the 4 time stages. If we want to solve the regression model for this point, we need to find the range, that within the range, the observation data has the influence to the regression point, but out of this range, the observation point has no influence. So that's the strategy for solving the local regression. We call it spatial-temporal weighted regression because we are considering both spatial range and temporal range. So because the here nearest things has the higher influence, so we adopted the weighting strategy that's closer and that's influenced by the distance. And here are the equations. I will not dive into the details of the equations and these algorithms because today I mainly will show you the using case and how to use it. If you are interested in the details of the strategy, you're welcome to check out the paper we just published as a discussion paper in the geoscientific model development. And the name is a spatiotemporal weighted regression model for analyzing local non-stationarity in space and time. I will post the link to the chat later so you guys can check it out. So next, let's see one case study. This case study is using the simulated data. There are 5 time stages: T0 to T4. T4 is the latest time stage. And there are 2 independent variables, x1, x2. Here is, I'm not showing the x1, x2, but only the coefficient, beta1 and beta2. And the y, you can treat it as a house price or dependent variable. And this is the constant coefficient, beta0. You can see it's changing across space and the time. And then we sample we take out some samples from simulated data. Using these samples, okay, yeah, this is the paper. Thanks, Marshall. He just posted the paper. Okay. Then apply the algorithm to the sampled data. Then we can compare the model result and the true model surfaces. Okay. Here are the comparison between our method and previous two published methods, GWR and GTWR. STWR is the one we developed. And here the x-axis is time, T0 to T4. So T0 means we only use the samples from T0. For T4, we used all the data from T4 to the very oldest time, to the T0. Okay. If you look at the T4, you can see the STWR has the highest R square on the left image. On the right image, this is the estimated standard error. The red one is the result from STWR. STWR has the smallest estimated standard error, which means this STWR is the best model here. Okay, then let's have a look at the comparison with the true value. So this is the true value here, the figure A1. And B1 is the prediction using STWR. This is the prediction based on the regression model. And this is the prediction using another method that's published called GWR. And here in the image B2, it's the error of the STWR, which is the value from B1 minus A1. And the panel C2 is predicted error for GWR, which is the value of C1, this image minus this one. And you can see from these two, B2 and C2, the STWR has smaller predicted error here, which means that STWR is a better model. Okay, so that's the simulated data. And then let's have look at the real world data. That's the precipitation isotope data. That's the data collected from October 29th to October 31st. That's three days. So sample once, 1 day. And that these cross plot from the area is northeast US, and these crosses are the sampled locations. So that's a precipitation hydrogen isotope, which is Y here. The model we created is Y equals beta 0 and influenced by the precipitation. PBT is precipitation, temperature, Tm is temperature, and elevation. Okay. Later, I will in the showcase I will show the code for running this case. Okay. This is the comparison. Okay. The comparison using different method. OLS is the ordinary least square, and the GWR, GTWR, and the STWR here. So these two lines are the R square. R square, you can see STWR has the highest R square, and these two lines are the sum of square error. STWR has the lowest one. So this is indicating that STWR is the best model among these. Okay. Then let's see the cross-validation. So the cross-validation, leave one out, cross-validation. The blue dots are the square error of using previous population, the algorithm GWR. And the red one is the one from our algorithm, STWR. You can see from the box plot that the red one has the lower square error. Means that STWR is the better one, better model. Okay, and this is showing the prediction using the model. So the top one is the prediction using STWR, and this image is the prediction using GWR. Okay. All right. This is the introduction of this algorithm. So next, let me show you the code and how to run this model. So Shona, do I need to break it here for questions or after the code showing?
Sorry, I actually just got bumped off until right now. But I think if everyone has if someone has a question right now, I think we can go ahead and ask them. And it looks like we have a question from Tobias Keller. And his question is, what is the difference between the STWR and the GWR methods? Oh,
okay. Thanks, that's a good question. So I didn't show the detailed difference because just hold a second. The main difference is that how do we treat the time distance? The time kernel here. So the time kernel in our method is, hold on. So, okay, GWR is the one that cannot take the, okay, hold on, there is a chat. Okay, that's another question. Okay, for the first question, the GWR is the model that first they did not take the time into account. That's only geographic weighted regression. And for STWR, we take the time into account. There's also another method called, or algorithm called GTWR that take the time into account based on GWR. The difference between the STWR and the GTWR is the way that we treat the time distance. We call it the time kernel here. Okay. So in GTWR, they only treat the time distance by time difference, say t minus t slash p. But here we treat the time distance not only by the time difference, but the value change rate here. Because we think that if the value change is very fast, then it is also influencing the regression model. So if you want to know the details of this time kernel, you can check out the paper that just posted from Marshall. Okay, did I answer your question? Keller?
I think so. Yep, he says thanks. So yep,
Okay.
I think you did.
All
So no other questions have popped up. So I think we can definitely move on to the next step then.
Oh, there's another question from chat. It's from Noah. Oh, okay. You guys can now see. Okay, it's private chat. Okay, but you can see from my shared screen is the question is, did you try to compare your regression model to deep learning like neural network? That's really good question. The answer is no, we haven't, but it's in our calendar. We plan to do that. Thanks. All right. So I think that's all the questions. Next, let's have a look at the showcase. So did you guys all install the software? I assume you did according to the configuration, this one. Okay, I just updated the Jupyter notebook that with some more comments. You can update that from the link I shared on the chat here. Here, let me see the chat. So this one, you can update this one. Update the Jupyter notebook. Okay. You can open this Jupyter notebook from the notebook folder here. This one. I just uploaded to the GitHub here. Notebook. This one here. The real world STWR D3 C. This one. Okay. All right. Then let's see this one here. All right, the first step is to import all the necessary packages. So you can run this here, click this, run this first section, Then write the second section. Okay, then this steps is to read the data. The data is from the hydrogen isotope data that's in this folder here. The real world data is here. So you can see it from the GitHub here, the SDWR data here, and real world data here. So it's this one, the precipitation isotope from D3. Okay, if you open this CSV, you can see it has the coordinates, longitude, latitude, elevation, because we created this model. The hydrogen isotope is influenced by the elevation, precipitation, and the temperature. And this is the Y here. And this is a time step you need, because you need to calculate the time differences from each observation data. So here we use the hour, is 24 hour, and there are 4 days, so 24, 48, and 72. These are the data from 3 days. And you can change this according to your data. So just to put your dependent variable here, and the independent variable, you can select as many as you can for the independent variables. These coordinates are necessary here. Okay. Then this section is just reading the data. Let me see. Reading the data. Here, this line, and this line, these 3 lines are, you can change according to your data. So this is the coordination, longitude and latitude. This is the column number. And this one is the independent variables, column number 2, 3, and 4. So here we only have 3, so it's I only selected these columns. And this one is the dependent variable, the hydrogen isotope from the spreadsheet here. This one. Okay. Then after read the data, this is running the model, SDWR model here. Let's run this one. It will take some time. If you do the configuration according to the instruction, you can run these without problem. So now if you have any questions, you can ask, because it will take some time to run this. Any questions so far for running the code or configuration?
Did anyone have any hard time with getting it set up on their system? That would be another good question. We could troubleshoot that right now. Okay, I'm seeing we had some problems with the Mac.
Okay, Shauna. So how do we do this? Allow him to share the screen, or?
Well, first question, how long is it going to take for your code to run?
Just finished.
Oh, it just finished. Okay, well, let's just go on to the next step. This is something we can address with Desiree at a later time.
Okay.
Or if we get another break. So maybe
Okay.
Desiree, if you wanted to think about how we can kind of characterize the issue that you ran into, maybe we'll have some time later or towards the end that we can actually address that. Thanks. Go ahead, Chao.
Okay, all right, thanks, Shana. So after fitting the model, then we can, no, after running this model, then let's see fitting the model here. Then I run this section. Okay, then these are the output. So here, the model type is Gaussian. That's the kernel type. The number of observations here, the optimal one is 182. And the number of covariance is 4 here. So here it shows both the global regression result and the spatial weighted regression result. We can compare these numbers. For example, the residual sum of square RSS here in the OLS is 52,000 something here. Well, that in the STWR here is 25,000. You can see it's smaller, means this one is better. And for the AICC here, that's comparison. That's comparing the model. AICC for the OLS is 698. Well, for the STWR here is 669, which is improved. Smaller AICC is better. And for the R square here, it's 0.763 for the STWR. Well, for the OLS, it's 0.502. Okay. Oh, here is the model. This is the model from STWR for the constant x0. What's the value, mean value for these variables? Standard error, mean, median, and max. Okay. The next one is to run the GWR model, only GWR, that's using the latest time stage, only the observation data from the latest time stage, which only has 73 data. Let's run this. Then this is the output. We can compare these numbers from the GWR and STWR. So here, the RSS here from the GWR is 33,000 something, but in the STWR is 25,000 something. And the AICC here is 685. And this one in the STWR is 660 something. Let me see. Here. So this STWR is better here. And the R square, STWR is 0.763. And GWR is 0.688. Okay. The next step is to do the prediction. So for doing prediction, you need other input. The input of the independent variables at the area that you want to do the prediction. So here, in this folder, data STWR real world data, these 3 TIFFs are the data for the precipitation, temperature, and elevation. These three TIFFs. So far you need these 4 input data. Okay. Then here in the Jupyter notebook, just read these 3 TIFF data. Here you need to make sure the profile of these 3 TIFFs are the same. Okay, then let's run this. this is the profile. That's the metadata for the teeth. Okay. Then get the transform and no data from the teeth. These are just the metadata. Okay, run this and then do the prediction. Let's do the prediction here and this section. Okay, the prediction will take some time, like several minutes.
Okay, so if it's going to be running for several minutes, maybe we want to hear a little bit more from Desiree, where she initially encountered her problems on her Mac. And are you running on a Mac right now, Chao, or are you running on a Windows machine?
On a Windows machine. So for Mac, the difference from Mac and Windows, one thing that you have to is this, the path. Let me see. Did you have problem of doing the configuration or running the code?
I got the directory right, because on Mac it renames it to your name. So I did change that, but it looks like just Anaconda is frozen up right now for a while.
Oh, did you try it before?
No, I haven't used Anaconda.
Okay. So did you successfully open the Jupyter Notebook?
Notebook didn't show up when I opened it. When I put in Jupyter Notebook, Notebook wasn't one of the options.
Did you install the Jupyter Notebook?
Yeah, I put that in.
Oh.
So I'm assuming it's just something between Mac and PC where I need a hyphen somewhere else. That was another problem I encountered I fixed.
Yeah, I think that may be the problem of getting the Jupyter Notebook working through Anaconda. Let's see. Not sure what he's saying. Okay. At which step of this configuration you have the problem?
I'm past that if you scroll down.
Okay.
I did have problems right there on step 4 for the pip install requirements. Wouldn't
Step 4?
install. Yeah, yeah, for this one.
But this one?
Yeah, I got to this part and conda install worked, and then all of the pips would install.
Wouldn't install?
Except for requirements.
Except for this one?
Yeah.
But this one is not working?
No, those 2 requirements did not install.
Oh, these 2 are not working, right?
Yeah, and then I did have to install a pip for nose for the nose test to work separate. I guess that's standard.
Okay. Let me so Shona, let me try to test it in the Mac again later and to see if I have the same problem. Okay.
Definitely. And we have everyone's email addresses, and we'll also have the Discord server. So we'll definitely have the opportunity to iterate on this. So, but it's really good to know kind of where we're encountering the issues. So thanks for pointing that out, Desiree and Nicole.
Okay, thanks. So Now let's see next step. See, just run this. After prediction, then this step is to write the output. So save the predictions. So if you run this, then you can find the result from the here. And the real world data folder, you can find the output folder here. There are two output here. Okay, one is from STWR, this one is using the GWR here. Okay, then let's plot these two. So run this section, you can plot the result from STWR, then run this section, you can get the result from the GWR. So these two plots are the one that I showed in the presentation. These two. Okay. So yeah, that's all the code. So if you want to adjust it to your data, what you need to change are the input predicted variables here and the observation data that here. That's from the spreadsheet. Okay. Yeah, I think that's all. We have plenty of time for interactive session. So anyone have questions, just post it or ask.
Yep, so if there are any questions, just feel free to type that into the chat for everyone or directly to Chao. It's a little bit easier if we go to everyone. Here we go, we got a first question here. And the question is, how did you split the data between training and testing?
So training and testing. Training and testing. So this is not using deep learning. So it's not the training and testing in that aspect, but there's one section that used a similar concept. That's the leave one out cross validation. Just pick one out, leave one out, and then do the cross validation. So not training and testing like deep learning.
Thanks, Chao, that's good to know. Great, did we have any other questions?
Oh, Chao, this is Marshall. Yep. Actually, I have a question.
Okay.
I know maybe I have mentioned this with you in our previous discussion, but I think in STWR, there's an assumption that all the observation points, their locations are fixed, right? Along
yes.
all those time stages.
Right.
But let's extend our source, because I think maybe the examples you showed us now is, I may call it a shallow time, because the units or the reference system you use are the, for example, hours, days, weeks, months. But how about we extend our source to deep time? If the reference system is millions of years, sometimes billions of years, and I know the location of the observation points may change, right? Along such a long time.
Right.
So have you thought about that to some extent? So if we were in this situation, can STWR still be applied, or there are some new strategies?
Yeah, thanks, Marshall. That's really a good question. I plan to apply this algorithm to deep time. So the time step would be 1,000 years or 1,000,000 years, and the continent is moving around. But I don't have any solution for now, but it's in my plan.
So Chao, I have a question. Have you guys published the paper on this yet, or can we expect to see that out soon?
Oh yes, it's right now it's a discussion paper. Here we submitted to the geoscientific model development, and that's the first paper. I don't know, it's kind of slow. You can see here we submitted last year. They received October last year, and they accepted for review on March. And they just there's one review coming back, came back, but they need another one, so they just extended the review deadline for several times. I don't know, we're just waiting.
So
and
it's still under review now?
Yeah,
interesting.
Yeah, it's a discussion paper, it's open, everyone can read it and comment it.
Okay, nice.
That's the first paper, and we have another paper that's in revision in the Journal of Computers and Geosciences. That's the one we when we treat the large amount data, means lots of data points, a lot of independent variables, it's slow. Calculating is slow, so we developed the parallel computing for that. That's a second paper
very nice.
submitted to Computers and Geosciences.
Great. So that was kind of be my next question, is what's next for this model?
Next could be the one like Marshall just asked, apply that to the deep time. And let me see, next, so Xiang, are you there? Xiang? Okay, he's not here. He has more plans for the next steps, but the one that important one is to apply this to the deep time.
Yeah, that's very exciting. Obviously, I'm very excited about that. But,
yeah, maybe we can apply that to the mineral evolution.
Yeah, that'd be really cool. Absolutely. Great. And so we have another question from the chat. And the question here is, can we apply this code for any data sets? For example, can we have input data such as time, space, and elevation, like a DEM?
Yeah, let me see. So I'm not quite understand the question. Do you mean the input that data as in the spreadsheet?
I think so. You wouldn't necessarily be able to put a DEM like that. And Farah, please feel free to unmute yourself and chime in if you'd like. I think you couldn't bring in a DEM that way necessarily, but
so
probably
like
with time and space.
Yeah, like this without the precipitation and temperature. Yeah, you can use this latitude longitude as the independent variable.
Okay, cool. Very interesting.
I don't know if I answered the question because I don't quite understand the question.
I think you did. Okay. Great. So another question is, can you recommend a resource for beginners on how to use Jupyter Notebook? This is a good question. And maybe some beginning resources for Python as well might be nice, if you could recommend.
Well, to be honest, I'm not quite familiar with Jupyter Notebook. Not Jupyter, I mean Python. I'm good at R, using R. So this one, I just learned this from a little bit here and there, not systematically. So my personal recommendation is that find a problem or find the question you want to solve and then using that as a start point, then if you have some, then you have a lot of questions, then you can Google what you can do. That's my tip. Okay.
Great. And Lucy just posted a link on GitHub on how you, I believe this is to the Python getting started, if I'm not mistaken, that Kelsey Markey did a little while ago. And yeah, Jupyter Notebooks are a really interesting tool. And I think what Chao said is right, is, you know, you kind of have an application that you're interested in using it for. And something that we've used it for has been, you know, being able to share code that you can actually run, and also use it a bit like a kind of a lab notebook, if you will. So you can really have, and you can see as Chao's pulling it up there, you can really have notes in there. So it's well-documented code. You can run it live in the actual notebook, which is really useful. And yeah, so it's really great for sharing and to be able to see what's going on there. And, you know, if you're iterating with someone who's maybe more experienced than you or vice versa, you can also help them kind of troubleshoot their code in a way that you can't if it's just on their local machine. So it's a great tool for sharing. And I think it includes, I don't know, it's like 40 something programming languages that you can install and use on Python. So it's a pretty useful notebook tool.
Yeah,
and as far as coding, I am by no means the expert coder on this call, but I'll put in my 2 cents. For R and for Python, I really like datacamp.com. There's certainly some more advanced ones once you get a little farther along, but I really like that for a beginner because you actually do the coding in the browser and they debug and troubleshoot for you in the browser rather than doing it on an IDE on your local machine where you have to troubleshoot it yourself. So my recommendation for very beginning coding is Datacamp. Great, thank you, Lucy, for putting that link in there. And there are others, but I really like Datacamp because it does you actually do it in browser rather than on your local machine. So that's very useful for those of us that are not so great at it. Great, so did we have any other questions? I think we're kind of getting towards the end. Were there any other comments or questions?
Oh, I can leave my email. Feel free to shoot me email if you have any questions.
Thank you, Chao. And as I mentioned earlier, we're going to have this up, but we're going to post it on YouTube, and we're also going to post it on the Discord server where we can actually have a conversation back and forth. So for those of you that maybe didn't follow along today, but want to do it again later, you of course can email Chao directly, but if you discuss it on Discord, then other people can see your conversation and maybe learn from the issues that you had. So I think we could definitely follow up with some of the issues that Desiree and Nicole pointed out that they were having. And if we could do that on Discord, that would be great. Also, Brennan has recommended mybinder.org, and he says it's great for an online hosted Jupyter notebook. Okay, awesome. So definitely check out those links. Nicole Meyer is recommending Data Carpentry. Yeah, that's, I've not used that one personally, but I've heard really good things about that as well. And so that's many free online worksheets for R and Python and some different coding languages. So I've heard really good things about that as well. So thank you. A lot of great resources. We'll actually want to think about, Lucy, is there any way you can you copy this chat? I think we've got a lot of good links in here that we may want to make available to the other folks. So if you wouldn't mind copying that, and I'll try to do that as well, just to make sure we get it. Thank you, Lucy. And great. So I think we can go ahead and wind this up now, unless someone else pops a question in there. Our next session is going to start at 1:45, and that's going to be Xiaogang from the Carnegie Earth and Planets Laboratory. And he's going to be talking about cluster analysis and its applications in geochemistry. So I hope all of you will be able to join us at 1:45, have a brief break, have some lunch, take a nap if you're on the other side of the world. And we'll see everyone back at 1:45. Thank you all, and a special thanks to our speakers and our presenters today. Thanks, everyone.
Thank you.
Kristen, I think you have to save the chat.
Yeah, I'm trying to do it as well, and it won't let me. Even though I'm a co-host, it won't let me.
Yeah.
You can copy it?
No,
Yeah,
it won't let you.
Yeah, it won't let you copy for some reason, which I think is
It
pretty-
should save automatically for Kristen, but just to make
Even
sure.
Control C not working?
No.
No.
Oh, bummer.
Yeah, it's I even tried right-clicking, and copy is grayed out.
Okay.
I've pretty much opened everything, so I think I'll
Okay.
have the links.
Okay, good. Yeah, that was a lot of, those were really useful links. That was nice, everyone kind of sharing those there.
Yeah, thank you, Shauna, Lucy.
Yeah, thank you. That was great. Thanks so much for doing
Yeah.
that. We've mentioned, I think I mentioned in the email at some point, I was hoping to do a workshop
Sure.
in the fall for Carnegie,
Yeah.
but I think we're actually going to end up doing that more in the spring. So kind of a
Mhm.
4D part 2, but more applied and thinking about an intro to data science. And I think this is something that could be a nice module that we could potentially run for that workshop if you were interested.
Yeah, definitely.
Because I think, I mean, it seems like people were pretty interested in using this. So,
Okay.
and definitely thinking about getting into, obviously I'm interested in the kind of the mineral evolution and distribution aspects of it. And if we can think about this with like the time element, that's really interesting. So,
Yeah.
okay, great. Do we know if Kirsten has copied the chat, or are we just good to, I think it's going to send to her?
I think I have all the links, so
Okay.
I think we're okay.
Okay, great. Awesome. All right, well, I'm going to pop off then, and I will see you guys a few minutes before 1:45. Thanks again, Chao. Really, that was great.
Thank you.
Joe.
Thank you. See you guys.
Okay, take care.